Instructor Carlos Plain of Durham School states, "Most certainly, I consumed my whole time on Earth cultivating a particular speculation of the universe. And as of now, the speculation is being tested. He welcomes this as it is how science advances. The James Webb Space Telescope, JWST, is disturbing much of what has been regarded as truth in cosmology for the new year. Another ultra-deep image reveals that many mistakes have been made in cosmology. The telescope, which was originally designed to show us the earliest stars of the universe, is becoming an adversary of the past perspective, potentially introducing an entirely new science. Not all experts are cowering in fear at these new realities. Various scientists embrace these new developments because it has long been evident that something was wrong with the old theories. The variations in the measurements of the universe's expansion speed alone should have shaken researchers' consciousness a long time ago. However, instead of correctly interpreting these warnings, many clung to old hypotheses. The cosmic microwave background, CMB, long considered one of the most settled pieces of evidence for the Big Bang theory, was emitted about 380,000 years after the Big Bang, when the universe had cooled enough for electrons and protons to form stable hydrogen atoms. This process, known as reionization, made the universe transparent to light. The CMB was first observed in 1964 by American physicists Arno Penzias and Robert Wilson, who were working with a new type of radio antenna technology. This discovery earned them a Nobel Prize and cemented their place in the history of astronomy. The CMB provides a snapshot of the early universe, with infinitesimal temperature differences that offer crucial information about the conditions shortly after the Big Bang. Scientists have used the CMB as a solid marker for the fundamental parameters of the material universe, such as the expansion rate of the universe. In the late 1920s, astronomer Edwin Hubble had already resolved this by finding that distant galaxies are moving away from us at speeds proportional to their distance, known as the Hubble law or Hubble constant. While Hubble did not have the advanced measuring tools available many years later, the discovery of the CMB led to a recalculation of the expansion rate, which was lower than Hubble's original figure. Later scientists recalculated it again using type Ia supernovae as standard candles, stable light sources that provide reliable measuring points. Estimates derived from the CMB suggested an expansion rate of around 67 kilometers per second per megaparsec, while estimates based on cosmic explosions yielded around 74 kilometers per second per megaparsec. What does this discrepancy in determining the expansion rate of the universe really tell us? Did you realize that this difference has been known since the 1990s? Researchers have long suspected that something might be wrong with the analysis of the CMB, the assessment methods, or even the very concept of the universe's expansion. The inconsistency in the measurements is known in science as the Hubble tension. The consequences of this tension are immense, suggesting that key aspects of our interpretation of the universe might be flawed. For a long time, experts were puzzled by this issue, but since the James Webb Space Telescope, JWST, became operational, it has provided scientists with extraordinary data that may shed light on the mystery of the expansion rate. Some of these ancient, mature systems, which should have theoretically started developing before the Big Bang, are overturning old cosmology. Researchers no longer discuss errors or discrepancies in measurement. They now speak of the greatest crisis in modern astronomy. Not only might the expansion rate be incorrect, but the very notion of the Big Bang itself is now under scrutiny. Images from JWST offer evidence of a universe that is entirely different from what we once believed. The Hubble tension was the first clue, but now experts who still have confidence in the old theories are faced with the difficult question. Do we actually know much about the universe at all? Various scientists now stand on the remains of their beautiful yet imperfect theories, exploring space with a sense of dread while grappling with their findings. Given this crisis in science, we must ask ourselves, what do we really know about the universe? To answer this, we need to understand how science functions. Theoretical scientists use a complex web of mathematical models, accurate data, and logical reasoning to draw conclusions from the general to the specific. Their understanding comes from a mixture of observations, experimental results, and speculative hypotheses. The term theory itself indicates that these are constructions and ideas, not absolute truths. The only reliable data we have are the images provided by telescopes, the sound waves and radiation captured by radio telescopes, and the latest data from neutrino detectors or gravitational wave sensors. With the James Webb Space Telescope, we now have an instrument that can separate the most ancient light into individual frequencies and analyze it in extraordinary ways. JWST can show us the composition of galaxies more than 13 billion years ago, the mass they contained, and how many stars were present. It can also recreate the shape and course of a galaxy's evolution. However, JWST has limitations. It cannot always definitively determine whether we are observing galaxies or black holes with massive accretion disks that shine as brightly as galaxies. We must face the reality that for a long time, our science has accepted too many possible outcomes as facts and dismissed alternative explanations. Research has long been confident in its accuracy, but the latest revelations from JWST offer vital clues that could replace old theories with new insights. As often happens in science, scientists are now waiting for new discoveries that are so astonishing that many experts struggle to formulate new explanations. These new findings are shaking the foundations of our understanding of physical science, unsettling many scientists. Our current frameworks of physical science are still largely based on Isaac Newton's work from the 17th century. His laws of motion and gravity formed the foundation of our physical understanding of the world and the universe for many years. Newton's laws governed the motion of objects under normal conditions and worked perfectly on Earth. However, in space, his ideas required expansion, which was largely done by Albert Einstein at the start of the 20th century. Einstein's groundbreaking theory of relativity, published in 1905, revolutionized how we interpret reality, showing that space and time are interconnected and depend on the observer's movement. His general theory of relativity, published in 1915, extended this idea with mathematical proofs of gravitational anomalies based on the bending of spacetime by masses like stars or galaxies. Einstein's theories have been successful in many areas, but he also knew their limits. He realized that his theories would never fully explain the universe and hoped for a unified theory, which he did not achieve. No other expert has succeeded in doing so to this day. Where is the missing piece? Wouldn't it be fascinating to know where it lies? Michio Kaku, a prominent astrophysicist from the USA, said in an interview that solving this issue would undoubtedly win a Nobel Prize. So, let's explore whether specialists may have overlooked possible misinterpretations, or whether our telescopes are to blame. Dark matter and dark energy are at the top of the list of suspects for the true causes of the cosmological crisis. Our current models of the universe incorporate the ideas that dark matter and dark energy make up about 95% of the universe. Yet neither has been directly observed, and their true existence has never been proven. They may not exist at all, requiring entirely different explanations for the universe's development and the behavior of galaxies. Alternatively, they may have properties we don't yet understand. One idea is that the true properties of dark matter and dark energy have changed over time, possibly revealing some kind of intelligence. Gravity is another theory that needs further testing. This force, which causes attraction through mass or the bending of spacetime, has not yet been fully demonstrated. The idea of spacetime bending originates with Einstein and has been confirmed numerous times, but we cannot rule out the possibility that gravity may behave in ways we haven't yet understood, or that another force might be responsible for gravitational attraction between objects. Over time, a number of constants have been established in cosmology and astrophysics, but the study of the universe has always been a journey separate from our ongoing quest for understanding and discovery. From ancient human efforts observing the stars to modern space telescopes probing the depths of the universe, each advance in theory and observation has uncovered new secrets while challenging established beliefs. The James Webb Space Telescope represents a leap forward in observational space science, designed to look deeper into the universe than ever before. One of JWST's primary goals is to study the cosmic microwave background (CMB) radiation with unprecedented precision. The CMB, often referred to as the afterglow of the Big Bang, provides a snapshot of the universe as it existed just 380,000 years after its inception. This relic radiation carries valuable information about the universe's early conditions, including its temperature variations, which are essential for understanding the formation of galaxies and large-scale structures. The discrepancy in the measured values of the Hubble constant, known as the Hubble tension, has been an ongoing challenge. Data from type Ia supernovae and other cosmological probes yield a higher expansion rate, suggesting that our current models may be incomplete or that there are fundamental aspects of the universe's expansion mechanisms that we still don't fully understand. Beyond the Hubble tension, JWST has the potential to reveal insights into other cosmological mysteries, such as the nature of dark matter and dark energy. These elusive components are thought to make up most of the universe's mass and energy content, but their existence is still hypothetical. As JWST continues to push the boundaries of space science, it offers the possibility of transforming our understanding of the cosmos. The advancements made possible by the James Webb Space Telescope, JWST, are not only transforming our understanding of the universe, but are also forcing us to confront some of the deepest questions in cosmology. As scientists analyze the data sent back by JWST, they are discovering that many of the assumptions held for decades, if not centuries, about the cosmos may need to be revised. These revelations are unsettling to some but exciting for others, as they offer a unique opportunity to revisit fundamental questions about the origin, structure, and ultimate fate of the universe. One of the most striking implications of JWST's discoveries is the possibility that the universe might be far older and more complex than previously thought. The telescope's ability to observe extremely distant galaxies, some of which formed just a few 100 million years after the Big Bang, is reshaping our understanding of cosmic evolution. These galaxies, thought to be mere infants in the universe's history, show signs of advanced features like spiral structures and multiple star formations, indicating that galaxy development may have occurred much more rapidly than earlier models suggested. This discovery is challenging the assumption that galaxies took billions of years to evolve into their current state and is forcing cosmologists to reconsider the timescale of cosmic history. Moreover, JWST is uncovering more details about the enigmatic first stars of the universe, objects that formed in the so-called cosmic dark ages, long before the first galaxies appeared. These stars, known as population 3 stars, are thought to have been the first generation of stars, composed almost entirely of hydrogen and helium. Understanding their formation and evolution is critical to understanding the processes that led to the formation of galaxies, stars, and heavier elements. Until recently, detecting these stars was purely theoretical, but JWST is providing the first glimpses of their light, which is offering new insights into the very early universe. This breakthrough may also help scientists determine whether the first stars were capable of creating the first black holes, which could be key to understanding the formation of supermassive black holes that reside at the centers of galaxies. In addition to these fundamental discoveries, JWST is providing valuable data about exoplanets, planets orbiting stars outside our solar system. One of the telescope's primary goals is to analyze the atmospheres of distant exoplanets to search for signs of habitability or even life. Using its powerful infrared capabilities, JWST can detect chemical signatures in the atmospheres of planets that are too faint or distant for earlier telescopes to observe. Already, researchers have begun to study the composition of exoplanetary atmospheres, looking for the presence of water vapor, carbon dioxide, methane, and other molecules that are associated with life as we know it. By studying these distant worlds, scientists hope to answer one of the most profound questions of all: are we alone in the universe? The potential for JWST to revolutionize our understanding of exoplanets is immense, but it also raises significant philosophical and ethical questions. If we do find evidence of life elsewhere in the cosmos, it will challenge our assumptions about the uniqueness of life on Earth. It could also spark a broader conversation about the future of humanity's role in the universe and how we might approach the discovery of extraterrestrial civilizations, whether they are microbial or more advanced. Such a discovery would not only rewrite textbooks in biology and physics, but would also likely have profound cultural and societal implications. As JWST continues to push the boundaries of what we know, it is also raising important questions about the role of science in shaping our worldview. For centuries, scientists have sought to answer the most fundamental questions about the nature of reality, using the tools available to them at the time. But as new technologies, such as the JWST, provide us with unprecedented views of the universe, it becomes clear that our previous models and theories may have been incomplete or even entirely wrong. The emergence of new data often leads to the formulation of new questions, and the process of scientific inquiry is in many ways never-ending. Each answer, in turn, uncovers new mysteries, compelling us to revise our understanding and push further into the unknown. This cycle of discovery and revision is the essence of scientific progress. It is the reason why science remains an ever-evolving discipline, constantly refining our models of the world and the cosmos. As we move forward into this new era of space exploration, the potential for breakthroughs seems limitless. And yet, the more we learn, the more we realize how much there still is to uncover. For all the exciting possibilities that JWST offers, however, it is important to remember that the telescope is just one tool in an ongoing effort to explore and understand the cosmos. Other observatories and instruments, both on Earth and in space, will continue to complement JWST's findings, providing additional perspectives on the universe's mysteries. Together, these efforts will help build a more complete picture of the cosmos, one that might one day answer the questions that have haunted humanity for millennia, such as, how did the universe begin? What is its ultimate fate? And, perhaps most intriguingly, are we truly alone?